All right, guys. So one of the things that we mentioned in the introduction video is that the two new ideal basic circuit elements that we're going to talk about in this chapter, the capacitor and the inductor, are both energy storage elements, right? We did derive for the inductor the IV characteristics, and we're actually going to use those in order to derive an equation that will allow us to calculate instantaneously how much energy an inductor is storing. So here, let's talk about inductors in the context of energy storage. Now, we're in physics. The definition of power, right? By definition, power is how much energy is being expended per unit time, or in the language of physics, the power is the time rate of change of the energy or the work. Now, this is in differential form. We can also rewrite this in integral form by multiplying both sides by dt, integrating both sides. So here, this is equivalently, the change in energy is equal to the power integrated with respect to time. Now, keep in mind that this power could be power of any kind. There could be mechanical power, it could be gravitational power, it could be anything else, but we're not interested in those types of power in circuit analysis as much as we are in electrical power. Now, if you happen to have any ideal basic circuit element where you know the voltage and the current, then the electrical power associated with that device, well, it's a product of current times the voltage. So notice that I can actually use that in this, in which case I get that the energy is equal to, without putting in the limits of integration, I times V times dt, like this, integrated. Now, this is as far as we could go, unless we knew the IV characteristics for the inductor itself. But we just found for an inductor, the voltage across the inductor is equal to the inductance times the time rate of change of the current. So notice that I can actually use this and replace it right there, which means that my energy is equal to I times L di dt times dt. I can rearrange this slightly. I can pull out the inductance because this right here is constant. And I can rewrite this as I di dt times dt. Now, we wrote these IV characteristics using the notation of Leibniz, as opposed to that used by Newton for the derivative, because they look like fractions, and it looks like that dt right there and that dt right there can kind of cancel out, and we can actually do a change of variable by using the chain rule and rewrite this in the following manner. So by the chain rule, we're doing a change of variable, and it is the inductance times the current integrated with respect to the current. Right? Now, in terms of the bounds of integration, these are dummy variables. Right? So I can put primes on both of these. My variable is going to go in the top bound, and in the bottom bound, I actually have my initial current. This is the current at t equals 0. But notice that this part itself is easily integrable. Right? This is like x dx or y dy. It's going to be 1/2 that variable squared. So here, my change in energy is equal to L 1/2 I prime squared, and I'm evaluating it at the top bound at I, at the bottom bound I naught. I can plug in those bounds and subtract the two, in which case I can rewrite this as 1/2 L current squared minus the initial current squared, like this. Right. Now, if we can agree that the energy stored in the inductor when the current is zero is also zero. So if current stored in the inductor is zero, and this initial current is zero, then this above equation tells us that the energy, and this is an instantaneous energy, in the inductor is equal to 1/2 the impedance times the current within that inductor squared. And this is literally coming from this equation here, where this I naught is zero, and notice that this is not a change in energy anymore. It is now just simply an energy. Right. This is what we actually wanted to get to. This is the major fundamental equation that tells you how much energy is stored in an inductor instantaneously. If you know the inductance, you know the current, then you can actually plug into this equation, and you will actually calculate the energy stored.